Power rule. So today we're going to examine a little about the power rule under calculus. We don't go into the specifics as to what are the power rules and when do we use it and so on. We could always examine that. We're going to look at three specific things today. How to use the power rule to differentiate one, a constant. You could think of a constant as a number, an integer, positive or negative. We're going to also examine a rational. And our rational is just a fancy word for fraction. Think of it as a fraction. Whenever you hear rational, think of fraction. And last but not least, we're going to look at how to differentiate using the power rule of a root. And when you think of a root, well, here we have an example, x under the square root sign, and that's basically a root. Right, let's just do a little recapping of the power rule, of course, before we start. So firstly, if we have, for example, and this is just the general way, the standard format, if you want to call it that way, ddx, and ddx, you have to be aware of that notation. That notation simply means that we are asked to differentiate x to the n, where x is a constant and our n is our index, right? And that index or power can be represented by any integer, number, whatever. Good. I also want to highlight this here, the ddx. ddx is our notation for differentiation. This is telling us that we have to differentiate, but sometimes we will also see y, or sometimes we will see f of x. Good. So whether we see f of x, or we see y, or we see ddx, all this is telling us that it is a function that we have to differentiate, right? The power rule simply states that if we have to differentiate x to the n, we simply bring the n in front, we multiply that by the x, the constant, whatever that was, and we take away 1 to the index. So the n goes in front, and we take away 1 from the index, and that is basically the power rule, simply put. Of course, sometimes you might have a variable in front of the x, like in this example here. They might ask us to differentiate ax to the n, and I'm only using algebraic expressions so that we'll get in general picture. We'll look at some examples in a moment. So here, if we have ax to the n, the concept is the same. The n goes in front, and we'll be multiplying that n by the a here in this case, and likewise then we just take away 1 to that index, and that will leave us with something like this. So we have the a times the n, remember the n is what was on top, and we take away 1. And once we do that, this is incorrect here, it's not supposed to be ddx here. When it reaches this point here, it's supposed to be dy. So at this point, it is dy dx, right? And that will be a times n to the x to the n minus 1. And this is just algebraically. Let's look at it using some numbers or something that we can relate more. So here we have two simple examples. We have x to the power of 4, and here we have 2x to the power of 3. So you can think of the x to the power of 4 as the first example that we had earlier when we had x to the n, and you could think of 2x cubed as the second example where we have ax to the n. So you could think of the a as a 2, you could think of the n, not think of, but that's what it is, the n as a 3. So going back to the first one, if we are to apply the power rule here, we simply again send the 4 in front, and that would leave us with 4x. Don't mind my handwriting. And remember, we take away 1, so that will be 3. So the 4 goes in front, and we take away 1 to the exponent, and that will leave us with 3. 4 minus 1, that will be 3. And in front here, remember, if we have an a, or we have a variable in front there, we simply multiply the 3 by it. So we bring over the 3 goes in front here. So 3 multiplied by 2, that will give us 6, basic arithmetic. And then remember the power, we take away 1. So that will be 3 minus 1. And that ultimately will be equal to, when we simplify that, that will leave us with 6x squared. Right? It's really and truly that simple. Everything will just be multiplied out. Well, you just perform your simple arithmetic there, and you end up with 2. And over here we have the same thing, just drawn it out a little. So we have 4x to the 4 minus 1. That will leave us with 4x cubed. That's what we have here, 4x cubed. And the second one, same thing again, dy dx is the 3. Remember, initially we had the 3, so the 3 comes in front. It's supposed to have the 2 here. We bring over the 3, so we're supposed to have a 3 here. So 2 times 3, that will give us 6x squared. That means the 3, we take away 1 from the 3, and we have the 6 when we multiply the 2 and the 3. And that's basically the gist of the power rule. So let us see if we could go to our content. So first of all, when dealing with a constant, long story short, you could think of a constant as any number, any integer. So you could think of 8, you could think of 7, you could think of 6, and sometimes you get questions like that. So you have y is equal to 8, you might have what, f of x. That's a function. I mean, it wouldn't be that straightforward, but f of x, let me try that again. Let's say f of x, ooh, I have to get used to this writing. Right. So you have, let's say, f of x, this is supposed to be a x, is equal to, let's think of something like x squared minus 7. We could have a scenario like that. So here we have two different scenarios where we have a variable and a constant. Well, both of them are constant. The 8 here is a constant, 7 here is a constant. And if we ask to find y prime, or if we ask to differentiate, of course, using the power rule, remember earlier I made a reference that d dx, let me just go back to that, d dx, y, and we had what? F of x. These are all written in the form that we have to differentiate. Good. However, when differentiated, each one of these will be converted, each one of these will change. So d dx will now become dy dx. And when we put dy dx, we simply mean here now that differentiation has taken place. D dx simply means that it has to be differentiated. Dy dx simply means that it is differentiated. Y is telling us that it is to be differentiated. After we differentiate, we say y prime. Y prime is telling us now that, okay, it is differentiated, or differentiation happened. F of x is telling us that that's a function that could be differentiated or has to be differentiated. After we differentiate it, we have f prime of x. So those are notations that we should be aware of. Call it recap. F prime of x is telling us that, okay, that function is differentiated already to the first degree, or first derivative, if I must be more specific. Good. Simple put, long story short, whenever we are differentiating a constant, we will always get 0. So if we have 8, that's a constant, so y prime is equal to 0. Good. Y prime is equal to 0. And there might be an explanation to that, which I'm willing to share with you shortly. Don't worry, give me a second. And then we have f of x is equal to x squared minus 7. If we have to differentiate this using the power rule, let me get rid of this here. I don't want us confused. Good. So if we differentiating in terms of x, the function f of x is equal to x squared, applying the power rule we have, remember, f prime of x now, so it's no longer f of x. Now it will become f prime of x, and this will be equal to, remember the power rule, so x squared, the 2 goes in front and we take away 1. So that will leave us with 2x. You could always go back in the video and you would go through it slower so that you could see what happened there. So I send the 2 in front. Remember, I send the 2 in front. There is nothing in front, so the 2 goes in front of the x, and then I take away 1 here. And we just established that whenever we differentiate a constant, we get 0. So that here is supposed to be 0. So f prime of x is really and truly 2x. No need to put minus 0. And for the enthusiasts out there, you might ask, why 0? Why 0? Okay, I think this plays a little with understanding the laws of indices, right? When we do indices, allow me to erase this again. You could always go back. When we look at the laws of indices, we were taught anything raised to the power of 0 is equal to 1. And that is a fact, a proven fact, right? Good. When we're dealing in calculus, we can say that x standing on its own is the same as having the x, the 8 with the x. So this is the same as this. So if we have y is equal to 8, is almost like saying the same thing as y is equal to 8x to the 0. And we know that x to the 0, because anything raised to the power of 0, is the same thing as 1. Therefore, is the same thing as just writing 8. And we don't have to put the 8x to the 0. But understanding when performing calculus why that is important is simple, because understanding this here will help us to appreciate more why do we get 0 when we differentiate a constant. And the knowledge is simple. The 0, so if we go to revert it like this, if we go to refer to the 8, instead of just 8, refer to the 8 as 8 to the x to the power of 0, and we apply the power rule, we will see that the 0 goes in front, and that will leave us with 8 times 0. Interesting. And then we have the x to the 0 minus 1, right? But the 0 minus 1 is really and truly irrelevant. This here really and truly doesn't matter, because we know that anything multiplied by 0 will give us 0. So at the ending of the day, we get 0 there. And that is just a brief example as to justify, perhaps I call it a justification, I could be wrong altogether, as to why when we differentiate a constant, we get 0. And again, we could do many examples, but the basics will remain the same. So if I have, again, let's say I have a function y is equal to x cubed plus 3. And these are very simple functions. It could get very much intricate and more complicated than this. If I have a function like this, to differentiate, again, using the power rule, y prime will be equal to, remember the rule, the 3 goes in front, the index goes in front, and then we take away 1 to the index. So that would leave us with 3x, and if we take away 1 from this index, we stay with 2. So 3x squared plus this here will become 0, because remember, just like we did just now, once you have a constant, it will become 0. And in maths, that 0 there is understood. There is no necessity for putting it there. So then that leaves us with just 3x. And that is our answer. There are many more examples we can do, but we're keeping it simple just to bring out the concept. Moving on. What if we're dealing with a rational? And remember, as I said earlier, think of a rational as a whole number. Sorry, not a whole number, a fraction. So a rational is simply put a fraction, right? And when we're dealing with a fraction, or when we think of a fraction, we generally think of a numerator and a denominator. Good? So supposing we have y is equal to this, and we are asked to differentiate this. To go about differentiating this using the power rule, there's only one thing we need to know, and that is converting or inverting a fraction. So 1 over x, if you go to write it in the inverse form, is the same thing as x to the minus 1. It is understood, again, that there is a 1 here. That is understood. So when we revert or we inverse this function, we are left with y is equal to x to the negative 1. And with that in mind, we could simply apply the power rule now. So the power rule, again, remember the basics don't change. The power goes in front, in this case the power is negative 1, and then we take away 1. Don't mix up the negative 1 from the inverse versus the negative 1 when you're applying the rule. They're not the same negative 1. So when we bring this negative 1 up front, we have negative 1. For the purpose of illustration, I'll put the negative 1, but it's not necessary to put the negative 1. The negative sign alone would do, really and truly. So we have that negative 1 there, and then we do some arithmetic here. Negative 1 negative 1. So negative 1 plus negative 1, let's put it that way, is the same as negative 2. And that basically wraps up the rational. And then, so that our answer is more plausible, as it is correct, this is perfectly correct, this is the correct answer. But a lot of teachers, lecturers, and tutors usually prefer the answer in a positive. So then we revert it back into the rational. And again, remember the concept is the same. So here we have the negative 1 over now we have x squared. So the negative 2 now, when you invert it, it will become positive. And that leaves us with our answer. Negative 1 to the x squared, positive x squared. Let's do a busy second example. So supposing I have another example. Supposing I have x, let me give a, so supposing I have f of x. Again, feel free to pause the video and solve it. You could easily solve this before I do it. You could stop right there and see if you could solve this before I give you the answer. Alright, good. So if we have this again, remember we're following the same concept. Once you delimit a rational, write your inverse function first so that you send your denominator at the top. The power, whatever power it has, it will become negative when it goes at the top. So this is the same as 2 into x to the minus 4. Right? It was positive 4 as a denominator. When it goes at the top, it becomes negative 4. And once we have this, we can now differentiate. So we could say now f of f prime of x. This x is very difficult to write. Right, so f prime of x, remember the rule, going back to the rule, the index goes in front, and you could think of that 2 there as the a. Remember that a we had earlier. So minus 4 times 2 here, that would give us negative 8. Hope I did not lose you there. And remember, then we take away 1 to that negative 4. Negative 4, negative 1, that gives us negative 5. And that is our answer there. And then, oh, sorry, I didn't put the x. The x is still there. The x ain't going nowhere. So minus 8x to the negative 5. And that is the same as, when we revert this again, we have negative 8 all over x to the 5th power. Easy does it. And that there wraps up our rational. Let me just give you one more to do on your own. So let's suppose I give you d dx. Say d dx is equal to 7 over x cubed. This is a 3 here. Again, you could pause the video, take time to do this. And then I start, remember, I invert first. So then I have 7x to the negative 3. Good. So 7x to the negative 3. And now that I have it in this format, I could differentiate. So now I could find dy dx. I could find x in terms of y. So my dy dx here would be now power rule. My negative 3 goes in front here, and then I take away 1. So negative 3 times 7, that will be negative 21. Good. My x remains there. Leave my x just there. And minus 3 minus 1 supposed to give me minus 4. And that is my answer. And last but not least, again, we revert it in the original form so that we could have a positive or more positive response. So that's negative 21 over x to the power of 4. And the 4 is positive once you put it back in the denominator position. Right? Our numerator here would be 21. And yes, this wraps up our rational derivative. And coming down to the end, last but not least, what do we do when we're dealing with a root? And think of a root as simple as this, the square root of x. Good. It is key to understand how to convert or what does the root say. So just like when we did the rational, we always also convert roots into index form. We put it in the index form to the power. And x, the square root of x is the same as x to the half. Good? X to the half. It is understood whenever we have a square root that this has a 2 power here, and when the x is standing alone, that there is a 1 there. So the 1, the power of the x, becomes the numerator, and the root power, for lack of a better word, becomes the denominator. So we have x to the half. And once we have x to the half, now we could apply our power rule. Yes, it is a fraction, but the concept remains the same. So we have x to the half, and what does the power rule says? We send the x in front. Yes, not the x, the index. So we send the index in front. So that leaves us with a half in front of our x. And we take away 1 from that index. So that's 1. Let's put it like this, 1 over 1, because we're dealing as a fraction. 1 over 1 in this case, let me work it over here. So a half minus 1 over 1 is the same thing as saying 2 over 2, because we're looking for common denominators. 1 over 1 is 2 over 2, because 2 over 2 is the same thing as 1. And this will give us common denominator. And then we simplify here. So we have 1 minus 2 at the top. That will give us negative 1. And 2 minus, well, denominator, we keep the denominator. I almost said 2 minus 2 is 0. When we're dealing with fraction, we keep the denominators and we compute the numerator. So our 2 remains the same. So this would be to the negative a half. Good. If you're not comfortable doing it like this, you could always do the traditional method, the traditional way. That's 2 minus 1. We will end up with the same answer, 1 over 1. And you find your LCM, which in this case would be 2. And then you go, 2 can go into 2 one time, and 1 times 1 is 1, minus 2 can go into 1 2 times, and then 2 times 1 is 2. And that leaves us with 1 minus 2, which is the same as minus 1 over 2, right? So either way you choose to do it, it's fine. It's supposed to end up with the same answer. And notice here now that our power is actually negative. So like we did earlier, we can revert this, and that will leave us with 1 over 2x to the half. And there is one more thing we could do to crumb this little cake here. We just write it as a root now. So that's 1 over 2 root x. Yes. And that does it for differentiating a root. Let's see if we could do another example. One more example. So supposing I have the square root. There was the square root I had? Yes. Well, no. Let's do another one because this one will be too easy. Let's say I have the cube root of x to the 4th. This makes things a little more interesting. Let's assume I said y is equal to this. Y is equal to the cube root of x to the 4th. Again, remember, the power of the root becomes the denominator, and the power of the constant or the x variable inside here becomes a numerator. So when I convert this, I have x. Remember, the denominator, the numerator is on the inside, and the denominator comes from the outside. So that is this here. If I must use an algebraic expression, just for you to at least keep it in your mind, let's say we have a here, and let's say we have b here. The scenario will always be this. So x is equal to, the a becomes the denominator. Remember, the root power becomes the denominator, and the b becomes the numerator. Or you could always think of a common example. A common example usually helps too, so you always remember that common example. So it's easy to remember that the square root of x is always x to the half. Think of this as a simple and common example. But why is this x to the half? Because the square root means that you have a 2 here, and the x alone means that there's a 1 there. So whichever way would help you remember, you would choose that way. So with that in mind, because remember it wouldn't always be the same, but however it comes, that's a fact that will remain, right? So when you leave it like that, then we have x to the 4 over 3 or 4/3, however you want to call it. And with this here now, we can apply our power rule. So our power rule here, we simply, again, y prime now, because we differentiating, we send our 4/3 in front. So that will be 4/3 x, and then 4/3 minus 1. And I could see that minus 1 there in this case to make my computation a lot easier as 3 over 3. Because remember, the aim here is basically to have common denominators. Once you have common denominators, it's very easy to compute, right? So with this here now, I have 4 minus 3, that will be 1, and the denominators remains the same, so that's a third. So 4/3 minus 1, or 3 over 3, that will give us a third. Good. And that makes sense if we understand how fractions work, right? And we could do one last thing here. We could make this back, we could put this into the root form, and that will be the same. Oh no, actually, as is there, this will be the same as 4 cube root 4 cube root of x, all divided by 3. Good. There's no need to put this here below, because as it is there, it's already positive. So there's no need to send it into the denominator. You keep it right up there. And again, if we go back to this rule, we're reverting now. So the denominator becomes a root power. The denominator becomes a root power, and the numerator becomes the x power. Good. And this will be a wrap for today's video. So don't forget, like, share, and subscribe. And feel free in the comment sections to list whatever topics you think we could look at next. And until then, see you all again. Goodbye.